Hi, everybody. This is some discussion for March 26th, Thursday. So Section 8.3 was due today, so please make sure you hand in Section 8.3 to me by email. Section 8.4 will be due on Tuesday. Look for the solutions online on the website, our regular website, Daniel-Salati or Daniel-Salati.xyz. Exam 2 on sections 8.1 to 8.4 will be on Thursday, the 2nd of April. And after talking with some of the other professors in the math department, we sort of said that, when giving an exam, take-home exam, that everybody should have roughly the same amount of time to take the exam as others. So that doing it over a 24-hour period is really not quite so advisable. So what we'll do is we'll do the exam from 5 to 7 p.m. on Thursday. So normal class time is 5 to 6:20. We'll do it from 5 to 7. I'll email the exam to you before 5 o'clock. Complete the exam, scan it, and email back to me by 7. Okay, and during the exam, you can call me with my mobile phone if you have any questions. If for some reason you can't do it at this time, let me know, and we'll try to find an alternate time, okay? I know everybody's things are kind of chaotic right now, so let me know, if 5 to 7 on the 2nd isn't going to work for you. All right. I want to go over some problems in the text. Section 8.3, number 37. It is a generalization of the main theorem in section 9.1. It was a little odd for, I think, the author to ask you to prove a theorem that's more general than the theorem of section 9.1 without using the theorem of section 9.1. So anyway, let's prove it using the main theorem of section 9.1, which is an important theorem. If G is a group and A and B are normal subgroups of G, this is that theorem, then if the set product of A and B is all of G and the intersection of A and B is just the identity, then G is isomorphic to A cross B. Okay, and then in number 37, this is replaced with any n. Right, so this subgroup is certainly normal in G, the subgroup with one element in it. So what happens if the intersection is a normal subgroup? Which it always is. A and B are normal, so the intersection of A and B is going to be normal. What if the intersection is not just one? Then what happens? Not this, but something different. 1 second. All right, so here's number 37. Say A, B, and N are all normal subgroups of G, right? And N is a normal subgroup of both A and B. Okay, so you have this diagram. A is normal in G, N is normal in G, B is normal in G, N is normal in A, N is normal in B. Okay? Suppose that the set product of A and B is all of G, just like up here. We assume the same thing. And the intersection of A and B is just any normal subgroup. It's always normal, but not just the identity. Then what happens? What happens is that G mod N is isomorphic to A mod N cross B mod N. Okay? Now, certainly this is true. The set product A mod N, B mod N, right, which is the set of all elements of A mod N times elements of B mod N. This is the right cosets for N with A and right cosets for N with B, which is equal to the set of all right cosets of N with product AB for A and B and B. Well, that's the set of all right cosets for N and G for every G and G. Why? Because the product of A and B is all of G. That's one of the assumptions. So this is just NG for all elements of G. Which is G mod N. Now let's show that A mod N is a normal subgroup of G mod N. The correspondence theorem that we proved last time was that A mod N is a subgroup of G mod N. but we want to show it's normal. Okay, and the proof for the fact that B mod n is a normal subgroup of G mod n is the same. All right, this is a little bit of a notational nightmare, but what, did I turn that off? No. This is a little bit of a notational nightmare, but here it is. So a right coset for A mod n in G mod n is of the following form for a fixed ng in G mod n. Right, so you take the subgroup A mod n and you multiply on the right by elements of G mod n. Right, by a fixed element of G mod n. So this is a right coset for A mod n. It's A mod n subgroup times an element of G mod n, fixed element of G mod n. And that's the set of all NA, NG for every A and A. Okay? I know it's a little funny looking, but that's what it is. So for every A and A, for every A and A, NA, that's the set of all of these guys, right? Times NG. Maybe let's write it out a little. Right? This is the set of all NA, such that A is in N, times NG on the right, which is the set of all, come on, NA and G, such that A is an element of A, which is the set of all right cosets, NAG, such that A is an A. Right, which is equal to the set of all right cosets like this. N just wrote it down. Which is the set of all N G inverse A G, like that, such that A is in A. Now remember, okay, left multiplication, right? Well, because A is a normal subgroup of G. No, because A is a normal subgroup of G, G inverse A, G. Right, because A is a normal subgroup of G, GA is equal to AG. Right, so GA is equal to A0G. So for every A in A, there is A0 in A, such that GA is equal to A0G. Right, so GAG inverse is equal to A0, so GAG inverse is an element of A. Okay, so G inverse AG is just some element of A. Furthermore, the function f of A equal to GAG inverse is injective. And, well, is a bijection. From A to A. Well, it's a permutation of A to A. You can show that, right? So, this up here, the set of all NG, G inverse AG, such that A is in A, is equal to the set of all NG A0 such that A0 is in A. This is just mixing around the elements of A when you it's called conjugating, when you conjugate like that. Okay, so so this is NG A0 for all A0 in A, but this is the set of all NG and A0 such that A0 is in A, but this is NG times the set in A0 such that A0 is in A, but that's A mod N. That's just all of A mod N. We'll write cosets. Right, so there it is. So that's actually a little tricky. Right, the right cosets of AN by NG is the left coset of AN by NG. Okay? Alright. Now, okay, so there's three things we wanted to show. Okay, A mod N times B mod N is all of G mod N. 2. AN and BN are normal subgroups of G mod N. 3. So let's show that A mod N intersection B mod N is just the identity. Is just the identity. Okay, you want to show that A mod N, right, where N is the identity. N is identity element of G mod N. And then after this, theorem 9.1, theorem from 9.1 implies that G mod N is isomorphic to A mod N cross B mod N. Right, after this you'll have, because that's what the theorem in 9.1 says, if G is a group with normal subgroups A and B, the product of the normal subgroups is all of G, and the intersection is the identity, then G is isomorphic to the direct sum. So here, A mod N and B mod N are both normal subgroups of G. We proved that. The proof for B mod N is the same. And the product of the two subgroups is all of G. And the intersection of the two subgroups is just the identity. So that's all the three ingredients we need there to apply that theorem. Okay? So now we just need to show that that this is just N. Okay? Well, say that Nx is an element of A mod N intersection B mod N. Right, that is Nx is an element of AN, so Nx is equal to Na for some A in A, and Nx is an element of B mod N, so Nx is equal to Nb for some B in B. Since N is a normal subgroup of A, right, Nx, which is equal to N or Na, since N is a normal subgroup of A, Na equal to Nb is an element, or Nb equal to Na, we'll say, Nb which is equal to NA is an element of A mod N. Right? That's an element of A mod N. So N I want to say NB equal to NA if and only if oh, no, I don't need to say that. Hold on. So since NA is equal to NB, one second, sorry. Okay. Since NA is equal to NB, right, NA equals NB if and only if, right, BA inverse is an element of N, which, right, is a normal subgroup of A, well, which is equal to A cross B, A intersection B, right? So, right, A inverse is an element of A, and BA inverse is an element of A. Say BA inverse is equal to A0 in A. So BA inverse equals A0, so B is equal to A0, A0A, A0A, which, right, these are both elements of A, so this is an element of A. So B is an element of A intersection B. And A is, similarly, A is B is an element. B is an element of A intersection B. And then since A intersection B is equal to N, right? A intersection B, which is equal to N. So B is an element of N. So NX, right, which is equal to NB, is equal to N, right, because B is an element of N as required. Okay, so that's that problem right there. Generalization of the main theorem in section 9.1. Also in section 8.3, we went over number 33. Okay, we went over this in the discussion last week sometime. It was a while ago. Let me see. When did we go over that? Was it here? Nope. It was here, maybe. Yeah, 8.3, 8.2, 8.2. There it is. 8.3, number 33. So we went over this on March 12th. Okay. On March 12th. Take a look at that. Consider also the following statement. Give a proof on your own. Okay, check that one out. All right, so let G be a group and in a normal subgroup of G. G mod n is abelian if and only if A inverse B inverse is an element of n for all A and B in G. Okay, so it's similar to, it's not number 33. This isn't number 33. Number 33 is discussing these products, the subgroup that is generated by all those products called the commutator subgroup. But this is kind of related to that and why the commutator subgroup is important. So show that G mod n is abelian if and only if n contains all products of that form. Okay. All right. So that's a couple things in 8.3. Here's something in section 8.4 I would like to go over. This is 8.4, number 29, and it asks you to prove the following. Let K and N be in Z with K and N bigger than or equal to 1, and K divides N. Let K and N be, saying this in a weird way, let K and N be positive integers with K dividing N. Show that Zn mod, the cyclic subgroup generated by K, is isomorphic to Zk. So K divides N, and you want to show that the cyclic subgroup of generated by K in Zn, but that's isomorphic to Zk itself. Okay? All right. So here's a proof of that fact. So we're going to do this by the first isomorphism theorem. So we can prove this by showing that this K, which is 0, K, 2K, remember it's additive group, right? Looks like that. That all the multiples of K, by the way, let's assume, say M is equal to N over K. So M is the quotient. 2K, 3K, all the way up to M minus 1 times K. Right, that cyclic subgroup of Zn is the kernel of a homomorphism F from Zn to Zk. Right? And then, we get our result because of a surjective homomorphism. Is the kernel of a surjective homomorphism F from Zn to Zk. Right, so, the first isomorphism theorem, that Zk is isomorphic to Zn mod the kernel of F, but that's going to be this. Okay? Okay, so, alright, so since K divides N, K is less than or equal, well, let's say it's strictly less than N. I mean, if K is equal to N, it's obviously true, right? since k is less than n, right, since k divides n, k is less than n. Okay, so every should we use? Every x in Zn can be written as x equal to kq plus r, where, right, division algorithm, 0 is less than or equal to r, less than or equal to k minus 1. Okay, also, for every, right, r in the set from 0 to k minus 1, there is x such that x is equal to kq plus r, right? Because k is less than n. K is less than n, so the numbers 0 to k minus 1 are in Zn, those integers, right? So the function f of x equal to r is a surjection from Zn to Zk. So it's a surjection. We didn't show it's a homomorphism. We just got to show it's a homomorphism. But once we show that it's homomorphism, then it's a surjective homomorphism, and so we get our result by the first isomorphism theorem. Okay. Now we need only show that f is a homomorphism. All right, so let x, which is going to be equal to kq1 plus r1, be in Zn, and y, which is going to be equal to kq2 plus r2, be in Zn as well. Okay, so two guys, and now we're going to show that fx plus y is fx plus fy. Alrighty. Fx plus fy is equal to, right, r1 plus r2. Well, it's equal to what? It's equal to r1 plus r2 if r1 plus r2 is less than k. It's equal to r1 plus r2 minus k if r1 plus r2 is bigger than or equal to. Well, it's equal to r1 plus r2. It's just equal to r1 plus r2. Fx plus y is equal to f of kq1 plus r1 plus kq2 plus r2 is equal to f of k q1 plus q2 plus r1 plus r2, right, which is equal to and here we'll do it in a piecewise fashion, r1 plus r2 if r1 plus r2 is less than k, or it's equal to r1 plus r2 minus k if r1 plus r2 is bigger than or equal to k. Yeah, I think, yeah, let's do it that way. Yeah. right? Fx plus y is f of this sum plus that sum, which is equal to that. Now, when applying the division algorithm to x plus y, right, either the remainders, the sum of the remainders stays less than k, or the sum of the remainders is bigger than or equal to k, but in that case, you take k, subtract from here, and clunk it into there, right? It's be k q1 plus q2 plus 1 plus r1 plus r2 minus k. Right? So this is equal to, so r1 plus r2 if f of r1, if r1 plus r2 is less than k. So that's equal to fx plus fy if r1 plus r2 is less than k. Right? It is equal to f of kq1 plus 1 plus r1 plus r2 minus k if r1 plus r2 is bigger than or equal to k. Right? If the sum of the remainders is bigger than or equal to k, then you subtract it from there, right? And then put it here. Right? So here we're done. Right? Fx plus fy. Well, actually, do we need to say all that? No, I don't think we need to say all that. Oh, no, we don't need to say it all. I'm sorry. Just erase all that, because we're... Right, it's just equal to this, right, which is equal to r1 plus r2, right, as an element of zk. It doesn't matter if it's bigger than or equal to k or less than k, right, because as an element of zk, it always becomes less than or equal to k, whether or not you have to subtract the k. But then that's just f of k q1 plus q plus r1 plus f of k q2 plus r2, which is equal to fx plus fy. That's it. Okay? It's just simple like that as an element of zk. Right? The elements of zk, instead of reducing it to be less than k, you could sort of unreduce it to be bigger than or equal to k if you have to. But anyway, that's going to be equal to this plus that, right? Which is fx plus fy. All right, so that's an interesting theorem. Zn mod the cyclic subgroup generated by the element k is isomorphic to zk when k divides n. When k divides n. So notice that when k divides n, it says that the order of k in Zn is m, where m is equal to n over k. All right? Okay, so that's just some discussion problems, and we will do the lecture, finish up section 9.1 after that.